Hello, Debbie here. Let's talk about some double angle identities. I want to know how to find the sine of twice an angle. So, tempting to say that maybe we just take 2 times the sine of that angle? Well, let's see. So if I choose theta is 90 degrees, let's see if that makes a true statement. All right, so substitute in, so I get sine of 2 times 90. And I want to know, is that going to equal 2 times the sine of 90? Right? So it's an identity, remember, if this holds true for every single angle, every angle. Okay, so if I can find one that doesn't work, it is not an identity. So here I simplify inside the argument. So I'm taking the sine of 180 degrees, which is 0. On the right, I take 2 times the sine of 90. The sine of 90 is 1, and 2 times 1 is 2. So they are not equal, therefore the sine of twice an angle is not equal to 2 times the sine of the angle. There are some angles which that might work, but it has to work for every angle that we choose. Okay, so how are we going to come up with this identity? Well, we're going to rewrite 2 theta as theta plus theta. So I'm going to say I want to take the sine of theta plus theta, which is 2 theta. And now I'm taking the sine of a sum, so I can use my sum identity for sine. So it says take the sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle. And I notice that I've got these two terms, which is just the product of sine and cosine. So I basically have 2 times the sine theta, or 2 times the product of sine theta and cosine theta. So here is my double angle identity for sine. Basically, we're saying if we have some angle theta and I want to find the sine of twice that angle, if I would multiply that angle by 2 and I want to know the value of its sine, I can simply find that by taking 2 times the sine and times the cosine of the original angle. Okay, so it works for things where I don't know the actual angle measure, and it also works for rewriting expressions and doing different things. So let's look and make sure this really works. Okay, so I'm going to choose theta as 60 degrees. All right, so the sine of 2 times 60, which is basically the sine of 120. Okay, so I'm saying, okay, the sine of 120, which we know, what's the sine of 120 degrees? Is root 3 over 2. Okay, so I should get the same thing on the right-hand side when I take 2 times the sine of 60 times the cosine of 60. So the sine of 60 degrees is square root of 3 over 2. The cosine of 60 degrees is 1/2. And when I multiply those, basically I get, doesn't matter how you multiply them. Let's say we multiply these two first. Makes no difference the order you multiply in. So I end up with square root of 3 over 4. So square root of 3 over 4, multiply across the top, across the bottom, and then I double that. Then I end up with square root of 3 over 2. So I can see that it does work for 60 degrees and it will work for every angle. The other thing we can do is we can evaluate expressions like this one and give an exact value. Okay, we can certainly put that in the calculator and get a decimal approximation, but we want an exact value. And 11 pi over 12, yes, an angle of 11 pi over 12 radians does intersect the unit circle at a point. However, I don't know the coordinates of that point. So that's why we say it's not on the unit circle, meaning that the coordinates of the point where it intersects the unit circle, we do not know the exact value of those. So I can't give an exact value for 2 sine 11 pi over 12 times cosine of 11 pi over 12. But I can use a double angle identity to rewrite that in an equivalent form that I can then evaluate. So I see that I've got 2 times the sine of an angle times the cosine of an angle. So whatever that angle is, we know this is our double angle identity, so we say that that's the same as the sine of twice that angle. So we can say it would be equal to the sine of twice 11 pi over 12. And when I simplify inside these parentheses here, I would get 2 times 11 pi over 12 would be 11 pi over 6. Okay, and I know the sine of 11 pi over 6, which is negative 1/2. So we're saying then that this expression here is equal to negative 1/2. That's our exact value. Now, you could check that by putting it in a calculator, and it would give you negative 0.5. But sometimes it's always not a nice expression like a fraction that's a terminating decimal. Okay, so what about cosine of twice an angle? Similar procedure. We rewrite 2 theta as the sum of theta and theta, and we apply a cosine of a sum identity. So the pattern, remember, is cosine, cosine, sine, sine. So it's the cosine of the first times the cosine of the second, and has a different sign than the original. So it's minus, and then it would be sine of the first times the sine of the second. And then if I rewrite that, I know cosine theta times cosine theta is the cosine of theta squared, or we write that as cosine squared theta. And this would be sine squared theta. So here's our identity for cosine of twice an angle. Now, be careful. This looks so much like a Pythagorean identity. However, it is a difference. The Pythagorean identity, remember, is a sum. Okay? So let's check to make sure this one works. All right? And I'm going to choose theta as 45 this time. So I know that the cosine of 2 times 45 degrees is the cosine of 90. And we know the cosine of 90 is 0. Okay, so when I put 45 into the right side of my identity, it should evaluate out to be the same. All right, cosine squared 45 means take the cosine of 45 degrees and square it, which the cosine of 45 degrees is root 2 over 2. And the sine squared 45 means take the sine of 45 degrees and square it. And the sine of 45 is root 2 over 2. Okay, so order of operations, square before you subtract. So if I square the square root of 2, I get 2. If I square the 2 on bottom, I get 4. Could simplify that. Square the square root of 2 over 2 again, I will get 2 over 4, and that results in 0. So it does check out. That it does work for 45 degrees and every other angle it would work for because it is an identity. Okay, so once again, let's evaluate an expression that I can't give an exact value for. I don't know the exact value of sine or cosine of 5 pi over 8. So I recognize that it's the cosine of some angle squared minus the sine of some angle squared. So I can use my double angle identity for cosine to rewrite that. And the angle that I'm dealing with is 5 pi over 8. So I can write that as cosine of 2 times 5 pi over 8. So if I multiply or double 2 pi over 8, multiply 5 pi over 8 by 2, I get 5 pi over 4. And I know the cosine of 5 pi over 4 is negative root 2 over 2, which is exactly what this should evaluate out to. If you put it in a calculator, you would get a decimal approximation. This would be our exact value. Okay, now we do have we can write other identities for cosine of twice an angle. And what we have the ability to do is write it so that we have an identity for cosine of 2 theta that only has cosine in it. So if I only know the cosine of the angle, I can find the cosine of twice the angle. Or I can write it in terms of only sine. And the way we can do that is by using our Pythagorean identity. And remember our Pythagorean identity, cosine squared plus sine squared equals 1, and our alternative versions where we can isolate or solve that for cosine squared or sine squared. Okay, so we're saying, okay, then I'm going to write this in terms of only cosine. So I'm going to replace sine squared theta with an equivalent form of my Pythagorean identity. So I have cosine squared theta minus, and remember sine squared theta is 1 minus cosine squared theta. So I can replace it, and now I just simplify that. Distribute the negative. So minus 1 plus cosine squared theta. And then I have 1 cosine squared theta plus 1 cosine squared theta is 2 cosine squared theta minus 1. So here is another identity for cosine of twice an angle that involves only cosine, which will be helpful at times. I can do a similar procedure then to come up with an identity, double angle identity for cosine in terms of only sine. So I'm going to replace cosine with an equivalent form of my Pythagorean identity. And cosine, remember, is 1, or cosine squared theta is 1 minus sine squared theta. I don't need parentheses because I'm not subtracting it from something. And I can see that I have minus 1 sine squared theta minus 1 sine squared theta will be equal to 1 minus 2 sine squared theta. So once again, these look very similar to our Pythagorean identities or equivalent forms, except for they involve a 2, whereas my Pythagoreans do not involve the 2. So that's one way I keep those straight. So we actually have 3 identities for cosine of twice an angle. All right, so here's the summary of our double angle identities. So you'll want to remember those or come up with a way of remembering them, or you could possibly regenerate them if you needed to.